Mankind has always had the need to create spaces and shelters, and so architecture has evolved seamlessly along with the growth in civilization. And as it grew, it aligned itself with the fields of science and technology. But equally, it was an aesthetic discipline. Hi, I'm Sneha Gupta, and in this episode of Building Blocks of India, we are going to explore various designs and patterns that populated architecture. And not just any patterns that are propelled by science. These will vary from the golden ratio to the idea of symmetry.
As we travel across India exploring architecture, it is clear that a huge understanding of mathematics powered much of our design. Wondering how? Well, ancient India had a great understanding of mathematics, and this propelled many facets of design. For example, buildings were laid out with specific proportions and ratios. One can see this in India, starting with the Harappan civilization, all the way till the modern city of Chandigarh. The famous ratio that echoes in architecture is known as the golden ratio. Let's quickly see how that works before we explore it in architecture. Take a line, divide it into two halves, A and B, so that the longer part divided by the smaller, which is A by B, is equal to the whole length, which is A plus B divided by the longer part A. So, A plus B divided by A is equal to A by B. And if we resolve this, we get this ratio to be 1.61803398874989484420. The digits go on, and do this number, which is usually called pi. It is usually rounded off to 1.618. This number is known as the golden mean. Historically, the number can be seen in the architecture of many ancient creations like the Parthenon. In the Great Pyramid of Giza, the length of each side of the base is 230 meters with a height of 146 meters. The ratio of the base to the height is roughly 1.5717, which is close to the golden ratio. Almost all ancient Hindu temples follow a set of design guidelines. Usually the height of the temple should be double its width, and the height of the foundation above the ground, with the steps equal to a third of this height. The sanctum sanctorum should be half the width of the temple, and so on. These guidelines translate into various interpretations of the golden mean. But the most famous example of the use of the golden mean is the Taj Mahal. As we can see, if we break up various sections of the Taj, the ratios will be close to pi, which is the golden mean. For example, the width of its grand central arch to its width, and also in height of the windows inside the arch to the height of the main section below the domes, all translate into the golden mean. Another common mathematical concept also inherent in the Taj is symmetry. The symmetry here is quite visible. This line down the middle splits the Taj into two identical halves. Let's look at the mathematics of symmetry in theory once, before exploring it in more detail in architecture. Mathematically, symmetry means that one shape becomes exactly like another when you move it in the same way, turn, flip, or slide. dashed lines below are not lines of symmetry. Though they do cut the figures in half, they don't create mirror image halves. So what we see in the Taj is a kind of symmetry known as line symmetry or mirror or reflection symmetry. Basically, the object here is reflected across a line like a mirror. A small detail in the Taj, the line of small fountainheads in front of the Taj divide the structure exactly in half to the mirror. Quite miraculous, right? Reflection symmetries also abound in the decorations made from precious and semi-precious stones inlaid on white translucent marble. Line symmetry like this can be seen in many monuments across India. The famous Sanchi Stoop, the Ellora Caves in Aurangabad, the temple at Rameshwaram, and India Gate. Another kind of symmetry, which is less common, is radial symmetry or rotational symmetry. This is largely symmetry about a central axis, as in a starfish or a snowflake. These are often seen on ceilings of all kinds of monuments, or in stained glass windows in churches. But one structure that we want to explore in more detail is the famous Lotus Temple in Delhi. This temple was made by the Baha'is. It looks like a lotus from the bottom with 3 rows of lotus petals containing 9 petals in every row. The outer set of 9 petals open outwards, forming 9 portals. Encircling the lotus-shaped structure are 9 pools which represent the green leaves of the lotus plant. Special building materials were used to build the structure. The white cement from Korea, white marble from the Pentelicon mines in Greece but cut in Italy, the concrete dolomite aggregates of Alwar mines near Delhi, and the white silica sand from Jaipur, India. The structure was built over a period of 6 to 7 years. From a frontal view, the structure is symmetric, but the symmetry really comes alive if we move up and get an aerial view of the monument. From the Baha'i temple, let us move to another stunning religious structure, the temples at Khajuraho. This temple is called the Kandarya Mahadev Temple. Now, if you look at the tower or shikhar, we see that they are surrounded by smaller towers, and then still smaller towers, and so on for many levels. Now, this repetition is a very complex form of mathematics called fractals. Very simply, a fractal is a never-ending pattern. Fractals are infinitely complex patterns that are self-similar across different scales. They are created by repeating a simple process over and over in an ongoing feedback loop. Now, if we look at the shikhar again, can't you see a fractal structure? There are in fact 84 fractals, ascending together and culminating at the spire. Each of these smaller towers is designed to look like a miniature reproduction of the whole. We can see this fractal pattern in a host of other temples, like the Virupaksh temple at Hampi and the Madurai Meenakshi temple. There's a philosophical angle to this mathematics also. Each fragment of the cosmos is believed to be whole in itself. And so the temples are designed and constructed as models of the cosmos. With this thought, let us move from a temple to a tomb. This tomb was built for the Mughal Emperor Humayun. Now, underlying the beauty of this tomb is a load of science and technology. Starting from the layout, the tomb proper stands in the center of a square garden divided into 4 main parterres by causeways, charbagh, which basically indicates a quadrilateral garden divided by walkways or flowing water into smaller parts. Now, the plan of the tomb itself is also. It is a square 9-fold plan where 8 2-storied vaulted chambers radiate from the central double-height domed chamber. The chambers of each level are interconnected by straight and diagonal passages. In Humayun's tomb, each of the main chambers has in turn 8 more smaller chambers radiating from it. If we wander through the tomb looking at the patterns, we will see a certain mathematical symmetry in them. These kind of patterns are called tilings or tessellations. We see them equally in other Mughal and Islamic monuments like Fatehpur Sikri.